simplify the model so that it should be simple model. At the same time, it has to give accurate solution. So this model idealization last week we started. Um, we discussed a few slides. Going forward, also we'll have a detailed discussion. This is a separate chapter. Once we are done with model idealization, we need to go for loads and boundary conditions. It is very important to give right loads and right boundary conditions. The reason is like you can give anything. You can, as you know, if you give junk in, it will give junk out only. Okay, so it is very important for us to define correct boundary conditions and apply proper loads, which represents actual physics. So this is also very important. Then we need to go for solution. We need to select some options. What are the options? Type of analysis, and various convergence issues and all those things. We will be addressing in solution options. Once it is solved, we'll go for post processing and reviewing the results. Okay. So this is the flow we generally follow for stress analysis. Okay. Once we have done the post processing, then we need to review the results. Okay. Then one of the thing is whether these results are making sense or not. Okay. So this will you'll be understanding based on your experience level and understanding the component behavior. Okay. When if you see like in operating conditions, um, if it is applied subjected to loading, how the model behaves. That physics we need to able to understand. Then only you can correlate with the analysis results. Okay, so there we need to judge whether these results are making sense or not. If it is making sense, then we'll go ahead and check calculate the margins. If not, calculate the loads and BCs. Okay, and review the. So if results are okay, then we'll go and check with the margins, whether this geometry is having good margins. If it is having good margins, then our analysis is complete. Even if it is not having good margins also, our analysis is almost complete. But we need to give that inputs to design team, saying that this geometry doesn't have a good margins. It requires a design improvement, or we need to redesign the component. So once it is redesigned again, it has to go for model idealization and it will go for all this cycle. So this is the general overview of the stress analysis. So here we'll see how we'll take small example how the design improvements make it will have good structural margins. So this example I have taken simple L bracket. Okay, um, it is subjected to 500 Newton loads. It is constrained at this location, and we have used steel material properties. Okay, Young's modulus, Poisson's ratio, and for steel it is yield limit is 500 MPa. So these are the things you have taken, and geometry wise, you have taken web width of 10 mm and bracket thickness of 2 mm. So here what we have done is we constrained here and applied load here. So here complete phase is applied subjected to 500 newtons. So it is very for us it is very important how to apply this load here. Okay. So here what I did is we can apply as a point load or we can apply as a pressure load. It all depends upon how you want to apply. But applying pressure load is more appropriate because it is subjected to uniform load. So we I try to apply as a pressure load here, which is having some reason. It is subjected to 500 newtons, and it is completely this area is subjected to uniform loading. So we have used plane stress with thickness. So these things we will discuss in detail, the types of elements and what is this plane stress plane stress elements in model idealization. So for this problem, we have taken plane stress with thickness elements. Then when it is subjected to load along this direction, so along this direction, So this component will tend to bend in this direction along x-axis, okay, or along normal to this bracket, this web. So this is the general behavior when it is subjected to uniform deflection on a bracket. So now coming to stresses, I have not plotted down three types of stresses. One is maximum principal stress, that is maximum tensile stress is 638 MPa. One message stress is 580 MPa, and minimum principal stress is 277. So this maximum principal stress or tensile stress is occurring at this fillet location. Okay, and compressive stresses are occurring at this top location. And when I try to check it, some disturbance is there. Now it's fine. Now it's fine. Hello. Hello. I'm hearing a lot of disturbance.
ఎక్కడి నుంచి వస్తుంది సౌండ్?
Hello, if you were, I think better everybody mute your microphones. Also, maybe it may be related to mobile, so please look into it. So please mute your mics. I think now sound is reduced. Okay. Okay. When we try to calculate margin of safety for this design configuration, then we got it at minus 0.22. So means this component is going to fail. It is having margin of safety a negative value. So it requires design improvement, or we need to redesign it. So going back to the things which we have considered is bracket thickness 2 mm and web thickness 10 mm. So what are the other parameters which can reduce the stresses? So if you see the stress, we are seeing very high stress at the fillet location. So here, can we redesign this fillet location so that it can reduce the stresses? So the baseline configuration it is having only 1 mm fillet. Now we'll go for a redesign with 2 mm. Okay, and let us see how the stress contours. Okay, now when I try to solve with the same loads, okay, for the improved modified fillet, the stresses came down from 638 to 504 stresses. Still, we are seeing negative margin of safety that we need to update design further. Okay, so when I try to increase fillet to 3 mm, then we could able to see the stresses reduction drastically from 638 to 440. And we have 1 minus is also 415 and S3 is minus 289. So our yield limit is 500. So all these three stresses are well below the yield limit. And if you take highest stress, maximum tensile stress, it is based on the maximum tensile stress S1. The margin of safety is 0.13. So to summarize this study, so baseline we are having 638, redesign 440. I think yeah, one more study we carried out, redesign 3 with increased fillet radius 4. So redesign 2 we are at 440 and redesign 3 we are at 407. So when I try to put together this summary table, so fillet radius baseline is having 1 mm fillet radius. Then we try to improve the design to 2 mm, then 3 mm on 4 mm. So overall, if you see the stresses changes from 638 to 407. And when I try to calculate, first two designs are having negative margins, but last two designs, design 2 and design 3, we are getting a positive stresses, 0.14 and 0.23. So this is how we'll generally perform stress analysis in sync with the design team. Basically, like in generally, some people will work both design and stress together, stress analysis together. Some people will work stress analysis separately and design separately. Analysis engineer, you have to do both the changes. Otherwise, as a stress analyst, you have to pass the information where the shortfalls are there and where we need to improve the design. So that recommendation and what are the margins you have to improve. If you give that inputs, and design team will change the necessary changes to the geometry. So maybe any questions I can take it up or chat. If you have any questions, just you can post it. So anyway, I'll continue for next topic. Or so last week we discussed about model idealization. So just I want to continue on this initial thing. So um, why we need to do model idealization? The simple reason is, in general, the structures or what are components we are going to analyze are very complex in nature, and it cannot be analyzed as is. If you try to incorporate everything in the analysis, it will take lot of computational power and human efforts. So we need to use some smart techniques so that model will be simplified. At the same time, results are not compromised. Okay. So idealization, model idealization typically depends upon several factors. The important things is degree of accuracy of the results, type of analysis, and type of loading. So these three things, most of the times it will drive the model idealization. Okay. For example, if you take this simple example, this is a simply supported beam. Upon it, there is a container resting on cross beams. Okay. So if you want to analyze this one, so one of the hard ways trying to model all these components. Okay, so but one of the smart way, if it is our area of interest is only this beam, then no need to model all this component. So all these components we can simplify it, taking simple beam and using the loads directly acting on the beam. So this is one simple example. Another example is if you take these blades, okay, fan blades. These fan blades are symmetrical, identical, and subjected to uniform loads such as omega, that is angular velocity, and is subjected to gas loads. Gas loads will flow uniformly for all the centrifugal, right, cylindrical, right. Gas flow will be uniform, and there will be some thermal gradients. Okay, so all these blades are subjected to uniform loads, both pressure, thermal, and um angular velocities. So, is it good to analyze all the blades when it is subjected to uniform loading? May not be. So, single blade is sufficient to do the analysis. Okay, that is a simple analysis. But when you want to solve a fan blade off, means releasing one blade, okay, impact event, then single blade is not a good idea. We have to use all the blades so that the impact of one blade releasing on the adjacent components we have to see. Okay, so that is the reason type of analysis is more important, and type of loading is also will drive. Okay, when loads are symmetric, we can assume a lot of things. When loads are not symmetric, then we cannot assume. So loading and type of analysis are very important while taking this model idealization. So, some more examples. If you see this rotor, this is the turbine rotor, and these are the blades. This is 2D representation, and this is 3D representation. Okay, this is the turbine blade and rotor assembly. So when you try to simplify this geometry, we have two ways. Whether we need to do 360 degrees or 2D is sufficient. For this complex geometry, can we do 2D analysis? Can we do single sector model? So there are three options here: 360, 2D, and sector. So which one we need to choose? This is very important. So when the problem is arrived, it is very much important for us to understand which location is critical for us. So is it blades? Is blades are critical, or blade attachment is critical, or turbine rotor is critical? So, so we need to understand. Suppose if turbine rotor is critical, then we can do this analysis. Simple 2D axisymmetric. We can go for 2D axisymmetric, and the blades are represented by some mass elements. Okay, one represents the blade mass, another represent loads acting on the blade, and these things are joined at the attachment region. This blue color represents attachment region, and we can do simple 2D analysis. Okay, it won't take much time, but only we need to accurately simulate blade and blade attachment region. Okay, so this will reduce a lot of computational power, and it will give results in a very quick way. So and and if it is our area of interest is blade attachment or blade, then we need to go for sector model. We need to take a simple single sector model, and we need to do the analysis. Okay. So here, similar to blades, these also subjected to uniform pressure, uniform thermals, and angular velocities. So all loadings are subjected uniformly all throughout the 360 degrees. So no need to consider complete 360 degrees. So if you want to solve 360 degrees model, it is only for one case. That is, again, it is for when blade is released. Okay, due to some assembly issues or failure issues, when blade is released from the assembly, at that time you need to consider complete 360 degrees model. I think we also discussed about this, but I want to give some emphasis on this because model idealization formulation is depending upon more on these things. So to determine generalize, we use Hooke's law to determine stress strain relationships in 3D also. So to understand, let us look into some three tensile tests conducted along X, Y, and Z location. Let us consider a material being pulled along X direction with the stress of sigma xx. When you try to pull this material in X direction, so along this direction, extension will be there. There will be elongation, and other two direction there will be compression because of Poisson's ratio. So same thing is represented here. Okay, strain is represented along xx. This is strain due to Poisson's effect, Poisson's ratio effect along y direction. This is the strain due to Poisson's ratio along z direction. Okay, so similarly, when you try to pull material along y direction, so there will be strain developed along y direction due to sigma yy. Similarly, there will be strain developed in x direction due to Poisson's ratio. Similarly, there is a strain developed in z direction due to Poisson's ratio. If same thing, like if you apply stress along z direction, um, strain will be developed in z direction, and Poisson's ratio is effect is seen in x and y directions. So when you try to combine all these strains, so if you try to combine sigma x will have three components. One from strain coming from stress along x direction. Then another component is coming from strain coming from y direction pull, and strain coming from g direction pull. So all these three are combined. Then when it is put together, it looks like this. Similarly, YY also it looks like this, and Z also we can combine like this. Okay, and the shear strains and stresses are connected by shear modulus, and they can be represented like this. Okay, so gamma xy is a strain, and tau is given by shear stresses. So when you try to put everything in matrix form, all these things in matrix form, so this is the strain vector, and this is the constant, and this is the stress vector. So this is a strain in terms of stresses. Now I want stresses in terms of strain. So when you rearrange these equations, these matrix, we can rewrite as like this. Okay, sigma xx, sigma yy, sigma zz in terms of strain in x, y, and z directions. Now they can represent in matrix form. This is also called as D matrix. So this is the stress matrix, strain, and this is the D matrix. And the G is given by shear modulus is given by E by 2 into 1 plus mu. So same thing it is put it in a better format. This is the D matrix representation. Okay. Now let us come to one dimensional. So now this is I'm talking about model idealization. Okay. So coming to one dimensional, for typical 1D problems, geometry is one dimensional along the length. Means suppose if you want to simulate a I beam or square beam, hollow beam, okay. So it can be represented by simple beam elements, and we need to assign cross section details. So the cross section details, suppose there are several beams here. So all these beams have unique cross sectional details. Okay, so we need to give cross sectional area of these beams, moment of inertia, and neutral axis details. So these are the details we need to give. Okay, when you try to solve using beam elements. So beams are geometrically 1D, but spatially 2D or 3D. So this is looks like this is simple line elements. Okay, 1D elements, but we need to give the 2D and 3D representation using real constants. So generally beam elements represents neutral axis of the beam. That means they are aligned along the neutral axis. Okay. Suppose if you take um, simple square cross section, the neutral axis will be at the center of the cross section, and these beam elements are aligned accordingly to the neutral axis. So beam elements are used for structures which are longer in one dimension than they are in other two dimensions. So this is also one other requirement. So similarly, there is a bar elements are also available. These bar elements are for bar elements we need to give only cross sectional area. No need to give other details. Now coming to two dimensional, um, generally the real life structures vary. Generally real life structures are three dimensional. So here the behavior will be independently along two or three directions. Generally, like if you see any structures, okay, it's a three-dimensional feature. and their behavior will be independent. They are not dependent on one dimension, means on the three directions. They are independent in all three directions, and we can make suitable assumptions about the variation in two or three directions. Um, that means like we can make some assumptions such a way that model will be very simplified. At the same time, results won't be compromised. Okay. So generally, the simplifications can be carried out in one dimensional, two dimensional, three dimensional, and finite element method will take care of these methods, these techniques. So as I mentioned earlier, this fourth point is very important. Every real life can be solved as every real life problems can be solved as 3D problem. So it is very easy to solve in 3D, okay? Because we no need to make any assumptions. Straight away import the model, do the meshing, and do apply the boundary conditions, solve it. There is no issues, okay? But the issue will be you cannot take it as is. If you take as is, it will be heavy and it will take a lot of time. And we cannot do quick design iterations as well. So coming to two-dimensional, a structural mechanics problem can be considered to be two-dimensional if a reasonable assumption about variation of unknown parameters in the third dimension. So if you make a reasonable assumption about third direction, we can take it as a two-dimensional. So in practice, we have three techniques available in 2D modeling. Okay, one is plane stress, one is plane stress strain, one is another one is axisymmetric. These are the three techniques we generally we use in 2D modeling approaches. So coming to plane stress, a structure if a structure is very thin, okay, compared to other two dimensions, then we can consider it as a plane stress problem. Okay. So one of the important considerations is loads will be applied in its plane. Okay. So if you take this component, so these two dimensions along x and y directions dimensions are bigger than the third dimension, and load can be applied only xy plane. So you cannot apply loads in plane or out of plane. Okay, along z directions you cannot apply any loads, and it assumes zero stresses through the thickness of the structure, zero stresses and non-zero strains. So it assumes zero stresses across the structures. That means along z direction there are no stresses. So some of these three are some examples. Okay, um, this is the thin plate, and this is some simple beam or bar. This is a plate with a hole. So all these three are good examples for plane stress. Now coming to the equation stress strain relation. Um, since thickness is small at the top and bottom faces are free from normal stresses. That means there won't be any stresses along z direction, and there won't be any strains along xz and yz directions. There won't be any shear stresses along xz and yz. There won't be any normal stresses along z. So these three factors will become zero. So once these things are become zero, then we can take this line out. Similarly, we can take this line out, and we can take this line out. Similarly, we can take these three lines out. So if you take those lines associated with the zero stresses in stress vector, then the equation looks like this. This in terms of strains in terms of stresses. Similarly, similarly the stress strain constitute relations. Stress stress in terms of strains is given by this. So this is the equation related to plane stress. Now coming to plane strain, the length of the member is much larger than other two dimensions. So the length of the member is much larger than the other two dimensions. Assume strains through the length of the member are zero. Okay. For example, dam subjected to water pressure. This dam length will be very high. Okay. And if you see how it will be simulated, so this can be simulated simple cross section area subjected to pressure loading, and the third dimension, which is very large, is represented by real constants. Okay. Similarly, this is for the pipe. Okay, pipe subjected to vertical pressure. So these two things are good examples for the plane strain. Normal so on the formulation front. So I have taken a strain and stress relationship here. So here strains will be zero along z direction, and the strains are zero along xg, and shear strains are zero along xg and yz. So if you make these three things zero, and if you take matrix associated lines associated with zero strains, then stress strain relation looks like this for plane strain problem. That is for plane strain, and the third one is axisymmetric. So this is also very important application in stress analysis, axisymmetric. So if a geometry of structure, material properties, loads and boundary conditions all are axisymmetric, then it is reasonable to assume that resulting deformation will also be axisymmetric. When a component is axisymmetric, geometry-wise axisymmetric, and it is having material properties, loads and boundary conditions, everything axisymmetric, then the deformed shape will also be axisymmetric. Then we can consider it as a axisymmetric problem. So one of the important other things are like in the axisymmetric assumptions, there won't be any variation in circumferential direction. That means if you take any cross section, the stresses will be uniform. Okay, there won't be variation. If you change, if theta equals to zero, cross section is having some stress. Theta equals to 30 degrees will also have same stress. Okay. And it is described by rotating a 2D cross section in 360 degrees around axis. It is so this is the axis of revolution. Generally, this is called axis of revolution. And if you take this cross section, if you revolve along that axis of revolution, it will form the 360 degrees of model. So you can take it simple, that cross section you can take it and do the analysis. Displacements will be constant in the circumferential direction. So there won't be any variation in displacement throughout the 360 degrees. And another important aspect is loading and deformation are confined to radial and axial direction. That is, loading can be applied only along the cylinder axis or radial direction. Okay, you cannot apply along theta direction. You cannot apply any loads along theta direction. So it is often used in analysis of pressure vessels, pipes, shafts, and aero engine rotors. So this is one of the example, pressure vessels subjected to internal pressure. This is general representation of axisymmetric problem. Okay. So some of the, if you take a cross section of the aero engine rotor, it looks like this, and blades and other things are simulated using some assumptions. So coming to axisymmetric, It is generally axisymmetric is represented by r theta z r theta z coordinates. R is represented by radius. Z represented by along axial coordinate along the axis. Theta is represented by circumferential coordinate. So these are the coordinates we generally use for axisymmetric. And coming to stresses, okay, sigma theta. Sigma theta stress means hoop stress, that is also called tangential stress or hoop stress, will be tangential to the uh, radius, okay, and radial stresses are along the radial direction, and g axial stresses are along the axis. And we have other shear stresses also, sigma rz, along this r and z directions. So these are the stresses acting on the in the axisymmetric problem. So in axisymmetric problems, the whenever it is trying to expand, whenever in a axisymmetric problem, it is subjected to internal pressure, it will try to expand. So any circumferential strains developed with any radial displacements, any radial growth happening in the axisymmetric problem will automatically develop circumferential strains. So let us see how it will be. Like if you see the original length of the cylinder is 2 pi r, and when you observe there is a radial growth, okay, so then it is elongated delta r, then new circumferential length will be 2 pi into r plus delta r. Then circumferential strain is given by difference between these two strains, these two lengths, that will give elongation by original length. So when there is a radial growth, automatically we'll get a circumferential strain. So a noteworthy difference with respect to plane stress case is appearance of hoop strain. Okay, so because this radial stresses causes radial displacement causes circumferential strain, then there exists a hoop strain. So that is the one difference between plane stress is appearance of hoop or circumferential strains. Now let us look into the axisymmetric formulation, how it can be simplified from the 3D problem. Because of symmetry about z-axis, the stresses are independent of theta. So all the shear strains and shear stresses associated with the theta will be zero. Okay, that we can take it out directly. Now it remains four factors here. One is radial stresses, axial stress, um, hoop stress or circumferential stress, then shear stress. Okay, we get this equation. So here we got additional equation hoop stress, because we get a circumferential strain or hoop strain due to radial deformation. So that completes today's session. So if you have any questions, please post it in chat. I can ask. I can try to. I can. I will try to clear your doubts. So any questions? Okay, I got response. No questions. I hope you have received materials. Okay. I'll try to send other materials also, maybe next couple of days. Okay. I think if there are no questions, then we'll call for today, and we'll meet again on Tuesday. We'll try to discuss more on model idealization techniques. So far we completed two chapters. We are looking into the chapter 3, model idealization techniques. Once it is complete, then we'll go for modeling and loads and boundary conditions and analysis techniques. So these are the textbooks we can use. You can refer while for this subject. So one is a Shigle, another one is Tirupati and Chandraputla and Bellagundu. Finite element analysis by R.D. Cook. This is very good book. You can refer to ASIS user manual when uh, when we work on finite element modeling. And you can also refer KJ Bate, which is also very good book. Okay, then we'll meet again Tuesday, and bye.